Hi. Okay, let's carry on with the topic of work power energy. From just now where we left off, we were talking about the energy equation, right? Being state 1 equals to state 2. Okay, and it depends on how you define where exactly is state 1. Okay, at which height you're talking about, at which point you're starting with. So state 1 is usually the initial, right? And then you look at what kinetic energy, what potential energy, and what spring energy you have. Okay, and kinetic it has a translational and rotational component as well. Okay, and potential energy, you have to define where is your zero potential energy level, which height. Okay, and then you calculate from there. State 2 is the same. Where do you define as the final state, and what KE, PE, and spring energy, and what spring energy you have at state 2. So by right, both should balance out with each other. Then you balance out, and then eventually you find the unknowns that you need to find lah. Okay, this is where we left off, but in fact what I want to tell you is the full version of the equation is not just the two values over here. Okay, the full version of an actual case is usually state 1 plus a work done is equals to state 2. Okay, this term work done, okay, is the extra thing that come in. When do you need to consider this? This one you need to consider when you look at things like losses, energy losses. Okay, losses from where? For example, from your friction. Okay, you get heat dissipated. Okay, friction, this is your loss. Okay, where else do you have work done? External forces. Okay, external forces. Okay, for example, in order for a box, for a wooden block to move along the surface, you need to apply external force, right? So this is your external forces. Okay, another example is your engine. Okay, in order for your car to move from stationary to a certain speed, right, you need an engine force. Okay, so this one can also be under work done. Okay, yeah, so these are the external forces. Even losses, the friction is considered an external force because the friction is actually a force applied onto the object. Okay, so under this circumstance, you will need to have a work done term over here. And the important thing is, this one, you must know whether it is negative or positive. Okay, so take for example, if you have an engine, right, the engine gives you that pushing force, right? Okay, it adds energy into the system, to the initial state of your object. So engine force will typically give you a positive work done. Okay, but if you look at friction, means from the initial state until the final state, along the way it loses friction, right? So the work done is actually a negative kind of work done. Negative. It takes away the initial energy. Okay, and it leaves you with the final. Okay, so that's why friction would be a negative energy. Okay, negative work done. So let's look at how this is being applied for in tutorial 2, question 5. Okay, you have a carton okay, moving along a surface. Okay, and this carton is 5 kilo and the speed is 2 meters per second, right? And it is going to encounter a spring somewhere, and this spring has a K of 800, okay, Newton per meter. So he's asking you for the compression. So find the value of X, how much the spring will get compressed. by this object. Okay, travel over here, it hits the spring, it compresses the spring by how much? Okay, so there are two scenarios. The first scenario is when the surface is smooth. Okay, when your surface is smooth, means what? Means there's no friction. Okay, so that means there's no external force. Work done by an external force, right, is actually zero. Okay, there's no other external force. There's nobody with a hand pushing the block. There's no engine inside this block, so there's no other external force. So that work done is equals to zero. So in that case, your equation will be safely state 1 equals to state 2. Okay, then the question is where you want to define state 1, where you want to define state 2 lah. Okay, so how we will define is like this. State 1 will be just as the object touches the spring. Okay, here as the object just happen to touch only, just touch only. The velocity, right, is still 2 meters per second. Okay, so this spring itself is still uncompressed. There is no X yet. So this would be your state 1. Okay, and then you want to know what? You want to know compression, right? Then of course your state 2 must be the point where the spring is fully compressed. And based on your previous understanding of the other question, when it's fully compressed, then the carton, the object, will stop moving. Okay, that is the place you see it moves, compressed already, then it stops. The next moment you know it's going to bounce back. Okay, it's going to bounce back. But we are not concerned about the bouncing back part. We are concerned about the point where it's stopped moving. Okay, so we have the carton here. Okay, so here, right, your velocity is going to be 0. It's not going to move, right? But your spring would have compressed by X amount. So this is your state 2. Okay, so then we look at state 1 and state 2. State 1, what do we have? We don't have potential energy for both cases because there's no height differences. So PE equals to 0 for both sides. Okay, KE. Okay, KE, there is a translational KE at state 1. Okay, spring energy, it is still not compressed, so there's no spring energy. So state 1 only have KE1. Okay, state 2, what does it have? Fully stopped already, there's no KE. Okay, there is only spring, which is your compressed. So spring energy 2. Okay, so this is your equation. So KE1 is simple, half mv1 square, and spring energy 2 is half kx squared. Okay, so 5 half times 5 times 2 squared is equals to half times 800 times x squared. Okay, then you will get your x to be 0.1581 meters. Okay, so this is the part A. Now part B is saying that your surface now has a friction coefficient of 0.3. Okay, meaning that as your spring no, not as your spring, as your carton okay, as your carton travels from the initial state to the final state, right? As your carton travels from initial state to the final state, it loses energy. Okay, so there is work done by the friction. Okay, so we can do this the same thing, but this time we have to do state 1 plus work done equals to state 2. Okay, So if we look at it, the same thing, KE1, there's only KE1 for the first case, and then there is only spring energy at the state 2, right? So now what is work done? Work done, it is supposed to exhaust the energy from KE1, okay? Energy is lost due to friction, so I will have to put a minus here, okay? Friction force multiplied by a distance. Okay, work done is force times distance, so friction force times what distance? X. X is the distance that was traveled from 1 to 2. Okay, so this is your equation, and we can also find what is F, what is your frictional force, because based on your friction equation, friction this would be what? This would be mg. Okay, so friction is coefficient times reaction, okay, and the reaction in this case is your mg. Okay, so here is half, okay, mv1 square minus mu mg times x equals to half kx squared. Okay, so this is your frictional force multiplied by distance. Okay, so you get half 5 2 square minus 0.3 times 5 times 9.81 times x, okay, equals to half times 800 times x squared. Okay, so here you will form a quadratic equation. And you will find your x to be 0.1408 meters. Okay, now does this number make sense? Just now, without friction, there is no friction, the compression is 0.158. Okay, which means the initial kinetic energy is able to compress so much of the spring. Okay, but now with the friction eating up the initial kinetic energy, right, you are left with a little bit less to compress the spring. Okay, so it is only natural that the spring gets compressed a bit less, okay, compared to 0.1581. So this one is logical. All right, the next video I will be talking about the full long question type of problem. Okay.